And I give you this formula directly because it requires calculus to work it out.
Is that density?
Yeah, I will give you explanation over here. The resistance of a wire equals rho times L over A. Okay, the rho is called resistivity. It's a constant for certain material. Okay, for example, you are using copper. Copper has a constant rho. If you are using aluminum to make a wire, therefore aluminum will have a different number of rho. And there is a table in the book. Okay, whenever you need a constant rho for the material, you can look it up. And L is the length here. And what do you mean by A? A is cross section. Cross-sectional area of the wire. Just like this picture. If you know the radius of this wire, how do you calculate the cross-sectional area? You know the radius.
2 pi r?
2 pi r? Or something else? What is 2 pi r? Area?
What you asking?
2 pi r, of course, is not area. Why? Area is meter squared, right? 2 pi r, just have r is in meters. There's no square meter, therefore it's not.
Pi r squared?
Pi r squared. That's the cross-sectional area. Usually, because all the wire, they are cylindrical, therefore the A basically equals this. Pi r squared. Oh, this should be in your memory forever. When your kids grow up, they ask you, Dad or Mom, what's the area of a circle?
Okay.
I have no idea. That's embarrassing, right? You have to know that.
Google it.
Yeah, exactly.
Oh, you say, okay, I Google it. I Google it for you, so now. Don't do that. Even you Google it, don't be in front of your kids, okay? All right, but most of the time, the R is not given directly. They tell you the diameter, right? Therefore, you have to do something to use it. And R is half of the diameter. Don't make a mistake that way, okay? It's an easy one. And that's the stuff below this title. Okay, we have a definition of a current, and we introduced the Ohm's law from the experiment, and also we have a formula to calculate the resistance of a cylindrical wire. There is one thing missed. I just want you to think about it. Look at this picture again. I labeled the current moving this way. But what do you mean? There are two types of charge inside, right? Positive charge and negative charge. But what do you mean by this direction? The direction for positive charge or negative charge?
No, it must be negative as electron.
Oh yes, of course. Only electron can flow. The protons, once they stay where they are, cannot move, right? Therefore, we have to make a decision over here. What is the direction of the electric current? If no such agreement, therefore people get confused when you have a real problem. And unfortunately, at Ohm's time, people, they were not clear about the structure of the material. They don't know atoms. They don't know the structure of atoms. Therefore, in their minds, positive charge can move, the negative charge can also move. They are equivalent. But now, they are different, right? Electron can move, but Protons, they can't. But even at Ohm's time, people realize there are two types of charges. You have to make a decision. What flow direction is the direction of current? And they made a wrong decision. They said the flow direction of positive charge is the direction of current. So after a few hundred years, do we need to change that? Oh, we understand that. We don't have to. We just keep it. Therefore, we know it's wrong, but we are still using it today. Okay? That's a convention. Therefore, I just write it down for you here. The flow direction of positive charge is the direction of current. It's a wrong decision, but we're still using it.
So the picture you drew, if the electrons are going the direction of the arrow, the current goes the other way.
Yes. If you said the electron going this way, the current goes that way.
Okay.
So therefore, that is I. And those things are electrons, okay? These tiny points are electrons, negative. Negative charge goes that way, current goes that way. Sometimes it's confusing, but I have told you the story over here, you better not confused. But that's okay in physics. Why? You know relative motion, right? Okay, let's try it. I am walking over here, right? So why I am walking? Relative to what I am walking? Floor. Basically, in your mind, you assume the floor doesn't move, right? Therefore, I am walking here. How about one small particle on my sweater over here? When I walking relative to myself, is this one moving?
No.
Of course not, right? Relative to myself, this one doesn't move. Therefore, one object is moving or not totally depends on the reference frame. You choose what is assumed to be motionless. Just like two cars on the highway, if they are moving at the same speed this way, relative to the ground, both are moving, right? But relative to this one, this car is not moving at all. Or you are the driver in your car, relative to the car, you are not moving at all. But relative to the ground, you are moving. On the same story over here, you know all the electrons moving this way. And somebody said, no, all the protons moving that way. Is this right?
No.
That's right or that's wrong, both.
Yeah.
If you assume electrons, they are not moving at all, therefore, the protons moving that way, right? So move or not totally depends on what you assume not moving. We call it reference frame. And the interesting thing is, the whole physics building is based on the simple assumption. The reference frame is the Earth. We assume the Earth is not moving. Based on this assumption, we have physics laws. If the Earth is moving, all the physics laws failed. Not work at all. Okay, so what kind of reference frame is good for physics? We call it inertial reference frame, which means whenever you choose something as your reference frame, that thing must have a constant velocity, either zero, either non-zero. If the object has acceleration, Can you choose it as a reference frame? No, you can't. If you choose an object which has acceleration as your reference frame, all the physics law failed. That's the truth. Okay? All right, let's take a break. 10 minutes.